Okay, ready for this?
Yeah, hit me.
We're diving into stabilized equal lower order finite element methods for simulating Brinkman equations in porous media.
Oh, wow.
I know, right? The title's a mouthful. But honestly, the research itself, way cooler.
I bet. It sounds like some serious fluid dynamics stuff.
It is. We're talking about how fluids move through the teeny tiny spaces in rocks, especially when there isn't much natural flow.
Huh, okay. So, like, imagine a really dense sponge, and you're trying to figure out how water moves through it.
You got it. And this is important for things like, well, extracting oil and gas,
Yeah.
or even for protecting groundwater.
Oh, that makes sense. So what kind of sources do we have for this deep dive?
We've got excerpts from the actual research paper, and while, yes, there are some equations in there, we're going to break it all down for you, and hopefully, have a little fun along the way.
Sounds good. So we're talking about fluid flow through rocks.
Yeah.
Why is this research so important? What's the big mystery they're trying to solve here?
Well, imagine you're trying to predict how oil will flow through, let's say, an underground reservoir. Or maybe you're trying to figure out how a contaminant might spread through groundwater.
Right, got it.
To do any of that accurately, you need to understand how fluids behave in these, really complex, porous environments.
Okay, yeah, I can see how that'd be tough. I mean, those tiny spaces in the rock must make things pretty complicated, right?
Absolutely. Simulating fluid flow through those microscopic pores is a huge computational challenge.
I can imagine it's like trying to map out every twist and turn in a giant underground maze.
Perfect analogy.
So how did these researchers tackle that then? Did they have to, use a supercomputer or something?
Well, they got pretty clever with their approach. They used something called finite element methods,
Finite element methods, okay.
which are basically mathematical tools for breaking down a complex problem into smaller, more manageable pieces.
Ah, so it's like dividing a giant jigsaw puzzle into smaller sections that are easier to solve.
Precisely. But here's the thing. When you simplify a problem like that, you sometimes lose accuracy.
Makes sense.
So the researchers came up with this really cool trick. They used something called the Galerkin least squares method, or
Yeah.
GLS for short.
GLS, okay, so is that like a safety net for accuracy?
You could say that. Think of it this way. You're learning to ride a bike, and you use training wheels at first to help you stay balanced.
Sure.
Those training wheels are like the GLS method. They provide extra support and stability while you're still getting the hang of things.
Oh, I get it. So in this case, it helped them keep their calculations accurate
Well.
even though they were simplifying things.
Exactly. So they've got their mathematical tools ready. But what about the rock itself? How did they create a virtual version of this porous environment?
That's where it gets really cool. They actually used real images of rock pores taken with a scanning electron microscope, or SEM.
SIM. Okay.
It's like taking a super detailed snapshot of the rock's internal structure.
Wait, so they used real images? That's awesome. I'm picturing a microscopic 3D maze.
Exactly. And they simulated water flowing through this virtual rock, comparing the results from different methods. They wanted to see, which ones were the most accurate and efficient.
Makes sense. So which ones came out on top? Did their clever tricks actually work?
They did. The GLS methods, especially the ones called VPD and VPDW, were like the rock stars in this study.
VPD and VPDW.
They were both accurate and incredibly efficient, which is, a big win in scientific computing.
So it's like they found the perfect recipe, adding just the right ingredients to make the simulation both faster and more accurate.
That's a great way to put it. There was another interesting finding. One of the methods they tested, called VPW, wasn't as stable as the others.
VPW?
Yeah. This was especially true when they were dealing with a simpler type of flow, described by something called the Stokes equation.
Hold on. So there's a simpler equation for some cases. When would you actually need the more complex Brinkman equation?
Good question. The Stokes equation works well when the flow is relatively straightforward. But when you have a more complex scenario, like fluid moving through a really tightly packed porous medium, that's when you need the Brinkman equation. You need to get a more accurate picture.
So it's like, choosing the right tool for the job. Sometimes a simple screwdriver works. Other times you need a power drill.
Exactly. And in this case, the Brinkman equation is the power drill, for those tricky, low permeability situations.
Makes sense. So they tested all these different methods, but did they discover anything truly groundbreaking, like, an aha moment, something that changes our understanding of fluid flow in rocks?
They did. And it all comes down to pressure. Remember those tiny spaces within the rock?
Yeah.
Well, as the researchers increased the speed of the water flowing through their virtual rock, they noticed something really interesting about the pressure difference.
Oh, interesting. So like the difference in pressure between where the water enters the rock and where it exits.
Exactly.
What was so interesting about it?
Well, they found that the pressure difference was much higher in the simulations that used the Brinkman equation compared to the simpler Stokes equation. And this wasn't just, a minor difference. It was significant.
Wow. Okay. So what does that actually tell us?
Well, it means that the Brinkman equation is much better at capturing the complex interactions between the fluid and the rock, especially, when the flow is strong.
Okay. So this pressure difference, why is it such a big deal? What does it tell us about how fluids actually behave in these environments?
Well, it tells us that, when it comes to real-world applications, the Brinkman equation gives us a much more realistic picture of what's happening inside the rock.
Okay, so that makes sense. So it's a big deal because it basically helps us understand like how to extract oil more efficiently.
Exactly. Imagine you're, let's say, an engineer, right? And you're trying to extract oil from a reservoir deep underground.
Yeah.
You really need to understand those subtle pressure changes to predict how the oil will flow, and how to get it out efficiently.
So this research is like giving engineers a superpower almost.
You could say that. It's giving them a more powerful tool, for
Okay.
sure. And it's not just about oil and gas,
Right.
This knowledge is useful for all sorts of things, like managing groundwater resources, or, even predicting how contaminants might spread underground.
Wow. Yeah. That's really important stuff. I mean, it's like we're getting a clearer view of what's going on beneath our feet, literally.
Exactly. And remember, we were talking about those different GLS methods.
Yeah.
Well, the fact that, VPD and VDDW perform so well, that's really encouraging.
Right.
It means we're getting closer to developing even more accurate and efficient simulation tools.
That's really cool. But wouldn't simulating like an entire oil reservoir be insanely complex, even with these faster methods?
You're right. Real-world scenarios can be incredibly complex. But that's where, the focus on computational efficiency comes in. Remember we talked about those lower-order elements?
Yeah, vaguely.
Well, they're kind of like streamlined versions of the math. And that helps make the simulations run much faster.
So even though they're simplifying things, those stabilization terms are there, making sure the results are still accurate.
Precisely. It's a delicate balance, efficiency versus accuracy.
Right.
And the fact that these methods can be run on, let's say, less powerful computers, that's a huge advantage.
Oh, yeah. I can see why.
It means more researchers can access these tools and contribute to our understanding of, these really complex systems.
So we've talked about oil extraction, groundwater management, but what about like the bigger picture? What are the long-term implications of this research?
Well, I think one of the most exciting aspects is, the potential to really improve our understanding of the Earth's subsurface. We're constantly learning more about how fluids interact with rocks and soil.
Right.
And this research, it's really pushing the boundaries of what we know.
So it's not just about solving specific problems. It's also about, expanding our fundamental knowledge of how the Earth works.
Exactly. And that knowledge can then be applied to so many different fields, from energy production to environmental protection.
That's pretty amazing. Now, I remember you mentioned earlier that one of the methods, the VPW, had some stability issues.
Yeah.
Can you tell me a bit more about that? Why is stability so important in these simulations?
Sure. Stability is crucial because, it basically ensures that the simulation results are reliable.
Okay.
If a method is unstable, you might get results that are, wildly inaccurate, even nonsensical. It's like trying to build a house on a foundation of sand. It's just not going to work.
So in the case of VPW, it just wasn't robust enough when dealing with that simpler type of flow.
Exactly. It showed promise in terms of accuracy, but it wasn't as, let's say, sturdy as the other methods. And that just highlights how important it is to, carefully select the right method for the job.
So it's kind of like choosing the right ingredients for a recipe. You need to know which ones will work well together, right?
Exactly. And just like with cooking, there's a lot of, experimentation and refinement involved in developing these simulation tools.
It's not just about plugging numbers into a computer. It's a lot more creative than that.
Absolutely. There's ingenuity involved for sure. And that's what makes this field so exciting. There's always something new to discover.
Yeah, that's cool. Now, speaking of challenges, I'm curious about the limitations of this research. I mean, are there any areas where future studies could improve on these findings?
Great question. And it brings up one of the most important aspects of scientific research, understanding its limitations. In this case, I'd say one of the biggest limitations is just, the sheer complexity of real-world rocks.
Right, because even those high-resolution S images, they can only capture a small portion of the rock's overall structure, right?
Exactly. Real rocks are incredibly diverse.
Yeah.
You have variations in pore size, shape, connectivity. It's like, comparing a single brick to an entire building.
So are you saying that we need to find ways to simulate fluid flow through, like, even larger and more complex rock structures?
That's definitely one area where future research could have a huge impact. Imagine being able to simulate fluid flow through an entire oil reservoir or, a large section of an aquifer.
Wow.
That would give us a whole new level of understanding and predictive power.
That sounds incredibly challenging. How could researchers even begin to tackle something that complex?
Well, one approach is to develop, new computational techniques,
Hmm.
techniques that can handle those massive data sets. Another approach is to find clever ways to simplify the problem without sacrificing too much accuracy, of course.
Okay.
It's a constant push and pull. Realism versus computational feasibility.
Right. And what about those pore geometries you mentioned earlier? Could those be a limiting factor as well?
Absolutely. Remember, those pores aren't just randomly scattered throughout the rock.
Yeah.
They're connected in complex networks that really influence how fluids flow.
So it's not just about the size and shape of the pores, it's also about how they're arranged and connected.
Precisely. Think of it like understanding the layout of streets in a city.
Okay.
If you know how the streets are connected, you can predict traffic patterns more accurately.
Oh, I see, yeah. So are you saying that we need to, like, map out those pore networks in more detail to improve our simulations?
Exactly. And that's where, advancements in imaging technology could play a big role.
Makes sense.
We need to be able to visualize those networks in 3D,
Uh-huh.
understand how they vary across different types of rocks.
So it's like creating a detailed roadmap of the rock's internal structure, which would then allow us to, simulate fluid flow with much greater accuracy.
Exactly. And that knowledge could have such a huge impact on, well, so many things, from resource extraction to environmental protection.
Wow. Now, we've talked a lot about the rock itself, but what about the fluids? Don't they play a role in how these simulations work?
They absolutely do. In this study, the researchers focused on, simulating water flow, which is a good starting point.
Yeah.
But in the real world, we're often dealing with more complex fluids, like, oil or gas.
Right.
And they have different properties that can really affect how they behave in porous media.
So simulating water flow is like, learning to play the piano with one finger. And simulating oil or gas flow is like playing a complex concerto.
That's a great way to put it. And just like learning a complex piece of music, we need to develop, more sophisticated techniques to accurately simulate those more challenging fluid behaviors.
So future research could focus on incorporating those fluid-specific properties into the simulations,
Yeah.
making them even more realistic and predictive.
Exactly. And that could lead to some really big breakthroughs in areas like, let's say, enhanced oil recovery or CO2 sequestration, maybe even designing more effective filters for water purification.
This is incredible. It feels like we've only just scratched the surface of what's possible in this field.
Yeah, for sure. But with all this complexity, all these challenges, is there a limit to how accurate these simulations can get?
That's a good question. It really gets to the heart of, scientific modeling. We always want more accuracy,
Right.
but we also have to remember that models are, well, they're simplifications of reality.
So no matter how good our models get, they'll never be perfect.
Exactly. There will always be factors that we just can't fully account for, like, tiny variations in the rock structure or unexpected changes in how the fluid behaves.
But that doesn't mean we should just give up.
Right.
Of course not.
Every time we get more computing power, better imaging technology, a deeper understanding of these complex systems, it all brings us closer to simulations that are more accurate, more reliable.
So it's like we're constantly refining our view of what's happening underground,
Yeah.
adding more and more detail. That's a great way to put it. And it's not just about scientific curiosity, These advancements, they have real implications for how we manage our resources, how we protect the environment, even how we understand the basic processes that shape our planet.
It's amazing to think that something as seemingly simple as, fluid flowing through rock can be so important.
It really shows how interconnected everything is, right? From the smallest pores in a rock to those huge underground reservoirs. It's all part of this one big, complex, fascinating system.
Well, I have to say, this deep dive has been incredible. I've learned so much.
I'm glad to hear that.
I feel like I have a whole new appreciation for what it takes to study fluid flow in porous media.
It's been a pleasure sharing these insights with you. And remember, this is just the beginning. There's so much more to explore.
So for anyone listening who's, feeling inspired, where would you recommend they start? What are some key takeaways they can hold on to?
I think the biggest takeaway is, well, to just appreciate the complexity and the importance of these processes that happen underground. Fluid flow in porous media might seem like, a really specific topic,
Hmm.
but it affects us in so many ways.
Right. It's about the water we drink, the energy we use.
Exactly. And I'd encourage everyone to stay curious, read about the latest research, ask questions, explore that amazing world beneath our feet. You never know what you might find.
That's great advice. Well, thank you so much for joining me on this deep dive. It's been truly enlightening.
It's been my pleasure. Keep exploring, keep learning, keep diving deep.